Hi Year 12 and welcome to Extension 2 Mathematics. This is our first topic, complex numbers. Now here's the topic outline. We're going to start with the complex number system and then we're going to look at representations of complex numbers, de Moivre's theorem, polynomials, powers and roots, and finish with regions in a complex plane. So let's start like we always do with mathematics with what we already know, which is the real number system. All real numbers can be drawn on a real number line, and that includes integers, including negative integers, rational numbers like fractions, percentages, and decimals, and irrational numbers like surds and pi. Now here's the real number system as you learnt it in Year 9. Real numbers are comprised of rational numbers and irrational numbers. Within rational numbers, we have the set of integers. Within the set of integers, we have the set of natural numbers. Now, you do need to know these symbols. The symbol for natural numbers is funny-looking N. For integers is Z. For rational numbers is Q. For irrational numbers, we write a Q with a graph next to it. And the symbol for real numbers is R. Now, let's quickly revise rational numbers. They can be expressed in the form A over B, where A and B are integers. That's what this means here. Literally, it says A and B are elements of the set Z, and Z is the set of integers. And also, B can't be equal to 0. So it includes integers, fractions, terminating and recurring decimals, and percentages. Now, irrational numbers cannot be expressed as a fraction. They are non-terminating and non-recurring decimals, and there are two types. There are algebraic irrational numbers, and that just means that they are roots of a polynomial that has rational coefficients, like x squared minus 3 equals 0. If you solve this, you're going to get x is equal to plus or minus root 3. And they include surds and logs. And the other type is a transcendental irrational number, and they cannot be found as roots of a polynomial, and that includes pi and e. Now let's look at imaginary numbers. When we solve quadratic equations where the discriminant is less than 0, we have to go beyond the real number system. So let's look at an example. We'll solve x squared plus 1 is equal to 0. We'll take the 1 over the other side. We get x squared is equal to negative 1, and take the square root of both sides. We're still going to get two answers, but neither of them are real numbers. Now, instead of writing the square root of negative 1, we're going to call that I, and we define I such that I squared is equal to negative 1. I is called an imaginary number, and it cannot be placed on a real number line. So let's return to our number system. You can see our real number system in here. Now, outside of that, I have the complex number system. And as well as real numbers, we have imaginary numbers. Now we're going to write Z is equal to A plus BI, because a complex number can have a real part and an imaginary part. And A and B are going to be real numbers. Now A is the real part of Z, and we write RE brackets Z. And B is the imaginary part of Z, and we write IM brackets Z. Now, if a complex number has no real part, we say it is purely imaginary, like 5i. And if a complex number has no imaginary part, then we say it is purely real, like the square root of 3, which leads us to an important point. All real numbers are complex numbers. It's just that the imaginary part is equal to 0. So let's solve a couple of equations that are going to result in complex numbers. Our first one is solve z squared minus 4z plus 13 is equal to 0, and we're just going to use the quadratic formula. So z is equal to minus b plus or minus b squared, take away 4 times a times c all over 2a. And tidying that up, we get 4 plus or minus the square root of negative 36 all over 2. Now we can simplify this. This is the same as the square root of 36 times the square root of negative 1. And that, of course, is 6i. We can simplify that, and we get 2 plus or minus 3i. Here's another example. This time we're going to use the method of completing the square. So we're going to write down the x squared and the minus 6x. We look for the term in x and the coefficient, and then we halve it, square it. So we don't need to worry about the negative, it's going to square out. So half of 6 is 3, 3 squared is 9. So I need x squared minus 6x plus 9. I'm going to borrow the 9 from that 10. Hopefully that makes sense to you. This is x minus 3 all squared plus 1 is equal to 0. Take the 1 over the other side and do the square root of both sides. And again, we are going to get two answers, plus or minus the square root of negative 1, which of course is I. And bringing the 3 over, x is equal to 3 plus or minus I. Now we're going to have a look at factorizing an expression rather than solving an equation. So z squared minus 4z plus 13. We're going to start by completing the square. So looking for the term in z, the coefficient is negative 4. Halve it, square it, gives us 4. So I'm going to borrow 4 from this 13. Now complete the square. That's going to give us z minus 2 all squared plus 9. Now I'd really like this to be the difference of two squares so that I could factorize, but it's not. It's the sum of two squares. So I'm going to do something sneaky. I'm going to change this plus 9 into negative 9i squared, because remember, I squared is negative 1. And now I can factorize by using the difference of two squares. We're going to get z minus 2 minus 3i and z minus 2 plus 3i. Two complex numbers a plus bi and c plus di are equivalent if and only if a equals c and b equals d. And remember, a, b, c and d are real numbers. Now this seems really obvious, but it's a really important point. Let's have a look at a quick example. Find the values of x and y if 2xy plus 3i is equal to negative 6 plus xi. So we're going to equate the real terms and the imaginary terms. So we'll start with the imaginary coefficients. We can see here that x must be equal to 3. And then we also know that 2xy must equal negative 6. Substituting in x equals 3, we get 6y is equal to negative 6, and so y is equal to negative 1. Okay, let's move on to operations with complex numbers. Now, complex numbers are a closed field. That means that any operation that you perform on a complex number is going to result in a complex number. So for example, we can say if we've got two complex numbers, z1 and z2, if we add them, we get a complex number, subtract them, we get a complex number, multiply them, we get a complex number, and divide them, we get a complex number. So here's an important point before we start. The real and imaginary parts of a complex number cannot operate with one another. So for example, 2 plus 3i cannot be simplified. However, real parts can be added and subtracted, and imaginary parts can be added and subtracted. So if we want to add complex numbers, then there's the rule. It's pretty easy though. If we want to add 3 minus I and 2 plus 2i, we add the real parts, so we're going to get 5, and then add the imaginary parts, which is I. So the answer here is 5 plus I. And subtracting is easy as well. So if we want to do 3 minus I, take away 2 plus 2i, then we make sure we put our second complex number in brackets, and we're going to end up with 3 take away 2 is 1, negative I take away 2i, which is minus 3i. Now let's look at multiplying. So we're just going to use FOIL. So we're going to go 2 times 3 is 6, take away 4i plus 3i, and here we've got minus 2 times I squared. And remember, I squared is negative 1. So it's going to be 6 take away 4i plus 3i plus 2, and collecting real and imaginary parts, we end up with 8 take away I. Here's another one, a perfect square. Now I would encourage you to learn how to do this in one go, rather than expanding this into 1 minus I multiplied by 1 minus I. It is 1 squared take away 2 times I times 1 plus I squared. And of course I squared is negative 1. So we get 1 take away 1, which is 0, take away 2i. So this particular question results in a purely imaginary answer. And then finally this one. This is the difference of two squares. So we're going to get 1 squared take away 4i squared. I squared is -1, so 1 plus 4, which is 5. Which brings us to the conjugate. Conjugate of a complex number, z equals x plus yi, is z with a bar on top is equal to x minus yi. And of course there are two important properties with conjugates, and they are that the addition or product of a conjugate pair of complex numbers is a real number. Let's have a look at that. So here's the addition, z plus its conjugate is equal to x plus yi plus x minus yi. You can see the imaginary terms cancel out. We end up with 2 times the real part of z. And then the multiplication, doing the difference of 2 squares, we've got x squared plus y squared. Here's an example. If z is equal to 4 minus 3i, show that z plus its conjugate and z times its conjugate are real. So z plus its conjugate is 4 minus 3i plus 4 plus 3i is equal to 8. And z multiplied by its conjugate is 16, take away 3i squared, which is 16 plus 9, which is 25. Now we're going to look at division, and we'll start by looking at the reciprocal of a complex number, which of course is found by inverting the number. So if we want to find the reciprocal of 1 plus 2i, that's going to be 1 over 1 plus 2i. Now of course we don't want imaginary numbers on the denominator, and the way to get rid of that is to multiply top and bottom by the conjugate. So one lot of 1 minus 2i is 1 minus 2i, and on the denominator I'm going to get 1 plus 4. And so our answer is 1 minus 2i over 5. And this process, when we make the denominator real, is called realizing the denominator. Now let's have a look at a division question, multiplying top and bottom by 3 plus 2i. Across the top we're going to get 6 plus 4i plus 3i minus 2. And on the bottom we're going to get 9 plus 4. You can see how I'm starting to move more quickly through these questions. So that gives us 4 plus 7i all over 13. Now we can write it like that, or we can separate it into 2 separate terms. Here's a past exam question, so already you can answer about 4 marks in the final exam. Let z equal 5 minus I. Part 1, find z squared in the form x plus iy. So z squared is equal to 5 minus I all squared, which is 5 squared, take away 2 times I times 5 plus I squared, which of course is -1. Tidying it up, we end up with 24, take away 10i. In part 2, find z plus 2 times the conjugate of z in the form x plus iy. So we're going to have 5 minus I plus 2 lots of 5 plus I. Which is going to give us 5 minus I plus 10 plus 2i, which is 15 plus I. And part 3, find I over z in the form x plus iy. So I over z is equal to I over 5 minus I, multiply top and bottom by the conjugate of 5 minus I. And let's expand. So here we're going to have 5i plus I squared, and on the bottom 25 plus 1. Tidying it up, we end up with -1 plus 5i all over 26. And I've split that into 2 terms. Okay, last thing for this lesson, and that's finding the square roots of a complex number. Here's our question. Find the square roots of 3 plus 4i. So we're going to start like this. Let 3 plus 4i equal x plus yi all squared. And x and y are real numbers. So we're going to expand out that right-hand side, and we're going to get x squared minus y squared plus 2xyi. And you can see how I've put the real parts together. So equating real and imaginary parts, we get that x squared minus y squared is equal to 3, and 2xy is equal to 4. And let's make y the subject here. Y is equal to 4 over 2x, which is the same as 2 over x. Now let's substitute this into here. So we've got x squared minus 2 on x all squared is equal to 3, which is the same as x squared minus 4 over x squared equals 3. Multiply everything by x squared, gives us x to the power of 4 minus 4 equals 3x squared. And that's the same as x to the power of 4 minus 3x squared minus 4 is equal to 0. Now let's solve this. It is an equation that is reducible to a quadratic. You can make a substitution, m equals x squared if you want to, but it's pretty easy to do without. So straight into two brackets, I'm going to have x squared minus 4 and then x squared plus 1. Now we can't solve this one. It would result in imaginary numbers, and we've already said that x and y are real. So x could be equal to plus or minus 2. Now we knew that y was equal to 2 over x, so substituting that into here, we get that y is either equal to 1 or negative 1. So we're ready to answer the question. The roots are going to be 2 plus I and negative 2 minus I. And remember, you can always check your answer by squaring it. Now there is a further question that's often asked, and it goes like this. Hence or otherwise solve the equation z squared plus iz minus 1 minus I is equal to 0. What we're going to do is use the quadratic formula, but be careful here, c is negative 1 take away I. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And tidying up under the square root, we end up with 3 plus 4i. And we were just asked to find the square roots of 3 plus 4i. So we're going to substitute in either 2 plus I or negative 2 minus I. You don't need to do both. Now working through the plus section here, we're going to get negative I plus 2 plus I all over 2, which is 1. And then through the negative I take away, in brackets 2 plus I all over 2, gives us negative 1 take away I. Okay, that's it. In our next lesson, we're going to look at representations of complex numbers.